A data structure looks like a place to store information. But that is the boring half of the story. The real question is, what future question are we making cheap? A good structure spends organization now so that lookup, insertion, deletion, or priority can be faster later. In this video, you will learn why data structures are time machines, how arrays and linked lists make opposite bargains, why stacks and queues control order, how hash tables buy fast lookup, and why heaps and trees organize data for priority in search. Start with the interface. A list promises positions. A stack promises last in first out. A queue promises first in first out. A dictionary promises lookup by key. The implementation is how we keep that promise cheaply under the operations we care about most. Computer scientists often separate the abstract data type from the implementation. The abstract idea says what operations are allowed. The implementation decides how those operations are made fast. A queue can be built with an array, a linked list, or a circular buffer. Same promise, different machine. Data structures are not judged by beauty. They are judged by operations. Can we find an item? Add one. Remove one. Get the minimum. Iterate in order. The right structure depends on which verbs appear again and again in the program. A beginner often asks, should I use an array, a list, a hash table, or a tree? A stronger question is, what will happen thousands or millions of times? If the program mostly asks for item number 7, direct indexing matters. If it mostly asks whether a username exists, key lookup matters. If it repeatedly asks for the smallest deadline, priority matters. Names are labels. Operation patterns are the real evidence. An array stores items in one continuous row. If the array supports direct indexing and you know the index, the address is easy to compute, so access is fast. That is why arrays are excellent when position matters, pixels in an image, daily temperatures, or the fifth element in a list. The trade-off is that inserting in the middle may require shifting many items. A linked list stores nodes that point to the next node. Inserting after known node can be cheap because we just change a few links. But insertion is not magically cheap if we first have to search for that node. Ask for item number 1000, and there is no address formula for that position. We have to walk node by node. The pointer links also cost memory and can be less cache-friendly than a tight array. This is the key mental shift. Arrays and linked lists can hold the same values, but they prepare for different futures. If the future is random access, arrays feel powerful. If the future is local insertion and deletion, linked lists may feel natural. Imagine a music playlist. If users mostly jump to song number 40, an array-like structure is attractive because the position is direct. But if users constantly insert songs after the current song, a linked structure can avoid shifting a long row. Same songs, different behavior, different best structure. The data alone does not decide. The future operations decide. A stack is a last in first out structure. The newest item is handled first. This is why stacks show up in undo systems, function calls, parsing, and depth-first search. A stack is a memory of unfinished work, ordered by recency. A queue is first in first out. The first item waiting is served first. Queues appear in printers, network requests, breadth-first search, and scheduling. The queue's promise is fairness by arrival order, do not skip the line unless the rules say so. A hash table uses a hash function to turn a key into a bucket index. Expected lookup means lookup is fast on average when the hash function spreads keys well and the table stays healthy. Worst case lookup can still be linear if many keys collide or an attacker forces bad keys. So the promise is not magic, it depends on spread, load factor, and collision handling. Sometimes two keys land in the same bucket. That is a collision. Good hash tables plan for this with chaining, probing, resizing, and load factor control. The goal is not zero collisions. The goal is to keep collisions small enough that lookup stays fast. The load factor is the ratio between stored items and available buckets. When it gets too high, neighborhoods become crowded and lookup stops feeling direct. A hash table usually responds by resizing, create a bigger table and redistribute the keys. Amortized resizing means the resize is expensive at that moment, but its cost is spread across many inserts, helping preserve the expected fast lookup promise. A heap is built around priority. It does not fully sort everything, fast top priority, not arbitrary search. It keeps a nearly complete tree shape, and it enforces heap order. Every parent is at least as important as its children in a max heap, or at most as important in a min heap. So a max heap keeps the highest priority item at the top, and a min heap keeps the lowest priority item at the top. This is perfect when we repeatedly need the next most important thing. A priority queue is the interface, a heap is a common implementation. The promise is simple: insert tasks with priorities, then repeatedly take the most urgent one. This powers scheduling, event simulation, Dijkstra's algorithm, and many greedy strategies. A binary search tree stores smaller keys to the left and larger keys to the right. Search becomes a sequence of decisions, go left or go right. If the tree stays balanced, each decision cuts away a large part of the remaining possibilities. A balanced tree preserves that few decisions promise. If it becomes unbalanced, the worst case can degrade to a linked list in disguise. That is the same having intuition we saw with logarithms, but now it is built into the shape of the storage. Trees can go wrong if they become tall and skinny. Then search becomes a linked list in disguise. Balanced trees protect the promise by keeping height under control. The structure spends maintenance work now to preserve fast search later. There is no champion data structure. Arrays, lists, stacks, queues, hash tables, heaps, and trees each make a different bargain. The mistake is asking, which one is best? The better question is, which future am I preparing for? A data structure is a prepayment plan. You pay with memory, constraints, maintenance, or slower updates so that important future operations become cheap. The cost is not gone. It is moved to a better time and place. Choose by asking 5 questions. Do I need direct access by position? Lookup by key? Ordered traversal? Repeated minimum or maximum? Frequent insertion and deletion? Then ask which operations dominate. A slow operation that happens once may not matter. A slightly slower operation that happens millions of times can define the whole program. Once the future operations are clear, the structure often chooses itself. Algorithms and data structures are partners. Breadth-first search needs a queue. Depth-first search naturally uses a stack. Dijkstra's algorithm needs a priority queue. Hashing changes lookup-heavy programs. The structure changes what the algorithm can afford to do. Here is the mental model. Data structures are not containers. They are agreements about future operations. Arrays by indexing. Linked lists by rewiring. Stacks and queues by order discipline. Hash tables by lookup. Heaps by priority. Trees by order decisions. In the next video, we zoom into hash tables. We will see why they feel like instant lookup, what collisions really mean, how load factor controls performance, and why a good hash function is less magic trick and more engineering contract.